Homework from last Thursday that we finally get to go over here, page 613, we had 1 to 3, 7 to 11. Requests to go over 3, 7, 8, 10, and 11. Let's go over number 3 first. What's the relationship between amperes and coulombs? Sometimes we see a question, the struggles that we have with it are just kind of, what are they asking? Not so much, I don't know how to do this, just I'm not sure exactly what they're asking. What's the relationship between amperes and coulombs? Not a crazy hard question if we know what they're asking. Okay, basically we're saying, look, an amp is equal to a coulomb per second. An amp is the rate of flow of coulombs. That's it. That's all they're looking for there. Rucker, was your hand up to answer the question? Okay. An amp is the rate of flow of coulombs. That's it. 7. How do the electrons in a loop of wire of a generator gain energy? That's a good question. And I'm not trying to throw a hint out there. I'm just saying that's a good question. There's a few good questions here. How do the electrons in a loop of wire in a generator gain energy? Well, tell me how essentially a generator works right now. Not the intricate details of a generator, but essentially how it works. Okay, the generator effect, okay, the thing that we learned on Thursday, right before Lenz's law. You got a wire, you got a magnetic field, you move one of them, and that generates an electric current. So how do the electrons in the loop of wire gain energy? Yep. Not forces of repulsion. What kind of force was it again? Let's draw a picture right here. Okay, we got, let's say we got a north pole right here, we got a south pole right here, and we've got a wire. I'll draw it like this. See this? I'm trying to draw that into the page there. Yes? Okay, it's supposed to be like an into the page wire. I just don't want to go an X or a dot because we don't have a current in it. It's just a wire. Now, in that wire, we've got electrons. I'll draw one of those electrons. Now, it's not moving. It's just a piece of copper wire in a magnetic field. But when we push that copper wire, let's say upwards, we push it upwards. It's moving upwards now. We get a negative particle that's now moving upwards. Okay, so as soon as you got a particle moving in a magnetic field, we use the hand rule for deflection. Thumb upwards, fingers from north to south, palm points out of the page. That electron starts experiencing a magnetic force out of the page, and that's what drives the electrons. So where do they gain their energy from? Ultimately, it's the kinetic energy from the movement of the wire. Right? It's the water falling over the dam and turning the turbine. It's the steam rising in the coal-fired power plant that moves the wire through the magnetic field. So where do they gain their energy from? Ultimately, it comes from the kinetic energy of the wire. That make sense? The kinetic energy of the wire, which in turn, along with the magnetic field, generates a magnetic force on the particles. Eight, a wire lying perpendicular to an external field carries a current in the direction shown below. It doesn't say electron current, but if it doesn't say conventional or electron current, we're going to assume electron current. In what direction will the wire move due to the resulting magnetic force? We're going to say thumb into the page. This is a deflection rule, right? Thumb into the page, fingers from north to south, palm's going to point upwards. So the magnetic force here is upwards. Do you see the difference between number 8 and what I just did right here? Number 8, we had a current. We wanted to see which way the force was on it. And this one over here, we applied the force. We pushed it, and we wanted to see which way the current was induced. Okay, which way the current started flowing as a result of the magnetic force. 10. Two conducting wires parallel to each other carry currents in opposite directions. Using the appropriate hand rule, determine whether the wires attract or repel each other. Those of you who were here on Friday and wrote the quiz, remember I said on Friday, one of the quiz questions was very much like one of the homework questions? You guys remember that? Okay, I can't remember exactly how that question was phrased on Friday. It wasn't exactly like this, but you can tell it's pretty much the same question, right? This time, we're told these two parallel wires are have a current in opposite directions. We want to know whether they attract or repel. So let's say that we got one current that's going into the page, one current that's coming out of the page. This will cause a magnetic field that points counterclockwise. This one causes a magnetic field that points clockwise. Now, we could draw the wires like this, okay, but as I told you on Friday when we were doing the quiz, it's easiest to draw them kind of looking at them at the ends. Okay, is that so far so good there? We haven't answered the question yet, right? We've just set the question up. We're told in the question that we've got two currents going in opposite directions, and that's what I drew. Now, if you want to find out whether they attract or repel each other, let's pretend they're little magnets. Let's pretend we got a couple of little bar magnets up here. If we did, then this would be the north pole of the bar magnet, and this would be the south pole, right? Because the magnetic field inside goes from south to north, and outside it goes back from north to south. Similarly, this would be a south pole, and this would be a north pole, because magnetic field goes inside from south to north, and outside from north around to south. Those two are going to attract or repel each other. Attract or repel, Brad? They're going to repel, because south against south repels each other. Now, somebody might say, well, why couldn't I draw the magnets down here, these pretend magnets down here? You could. South, north, north, south. North and north repel each other. Somebody else might say, why couldn't I draw them right here? You could. South, north, south, north. North repels north, south repels south. So it doesn't matter where you draw them. There's going to be a force of repulsion. Is that okay? Is it okay, especially for the people that weren't here on Friday, to experience that question with the quiz? Because for the rest of you, you guys have had it explained to you twice now, right? But 5 or 6 of you have only had it for the first time here just now. And finally, question 11. A wire that is 50 centimeters long carries a current of 0.56 amps perpendicular to... Perpendicular means that we can use what we've learned, right? The hand rule, the equations. What's the magnitude of the force? We're just going to say F is equal to ILB here, right? 0.56. Make sure that you make the wire length in meters, 0.5, and the magnetic field is 0.3. 0.084 newtons. Good? We just went over 5 questions. You guys comfortable with those 5 questions? Yes? Okay, because one of them, at least one of them, is essentially on your test.